Everybody wants software that automatically updates the design when changes are made. However, if not done correctly, automatic updates can generate just as many errors and omissions as they eliminate. To maximize the benefits of automated updates, the software must remember the engineering decisions that went into the creation of each element. If the engineering decisions are not remembered, the software will have to make assumptions when updating elements that could lead to errors. The OpenRoads technology is built to remember your engineering decisions. We call this design intent. For example, consider a center line and two edges of pavement. These are three independent elements, but have a relationship with one another that we as designers understand. The need is to get the software to understand that same relationship. Design intent captures the engineering decision that the edge of pavement is offset from the center line by some distance. Therefore, the center line moves, the edge of pavement also moves, maintaining the same offset distance. Without capturing the design intent, the edge of pavement would not move when the center line geometry moves. The scope of this class is focused on geometry and we'll discuss design intent in that context. However, design intent is not limited to geometry. The OpenRoads technology uses design intent throughout all aspects of the software to maximize the benefits of automated updates. Now that we understand the importance of design intent, how do we communicate it to the software? OpenRoads technology retains design intent by storing rules and relationships with each element. The easy part is that the software automatically captures what you do and creates the rules that define how each element is created and its relationship to other elements. These rules are stored with the elements and used to make automatic updates following your original design intent whenever changes are made. The challenging part is creating elements in a way that the rules properly replicate your design intent. Consider a centerline alignment made of two lines connected by an arc. This can be created in several methods that are all correct and valid ways to construct the geometry, but each result in different rules, which in turn results in different behavior when changes are made to the geometry. In workflow 1, create two lines, and then we create an arc in between those two lines. In workflow 2, we create the first line, then we create the arc coming off of that line or element, and then the last line comes off of that previous arc. Both workflows define arc by a radius and result in the manipulator to edit the radius, but when the radius is actually changed from a value like 100 to 150, the arc length adjusts and the lines retain at the original directions. However, when the radius in the second method is changed to 150, the direction of the second line changes. What happened? The rules or the design intent are not the same for the different creation methods. The first method resulted in rules that held the entrance and exit direction of the arc constant. The length of the arc changed when the radius was changed. The second method resulted in rules that held the entrance direction and the arc length constant. Here, the exit direction changed when the radius changed. As we just saw, the geometry tools used influence design intent. Design intent is also communicated using microstation snaps, Civil AccuDraw, and microstation manipulation tools like trim to element. Microstation snaps are a very powerful way to communicate how elements are related to one another. By snapping one element to another, we communicate our intent that these two elements always remain joined. Or we could use perpendicular snap to communicate our intent that one element is going to be perpendicular to another element. For example, consider a side road center line that intersects a main line. Assume for now that our design intent is for the two center lines to always meet at a perpendicular angle. The side road in the left image was created using perpendicular snap to communicate the design intent where the two lines intersect. When the direction of the main line changes as shown in the lower left image, the direction of the side road changes to remain perpendicular and the length changes to intersect the main line. Contrast that with the images on the right where the side road is created independent of the main line, where no snaps were used. When the main line direction changes, the side road is not altered. However, notice the side road extends beyond the main line. The microstation modify commands such as trim to element are also a powerful way to communicate design intent. Staying with the side road example, what if our design intent was for the side road to be at a fixed direction, not perpendicular to the main line? Creating the side road geometry without the snap produces the desired result, except we want the side road to stop when it intersects the main line. The Trim to Element tool will shorten or extend the side road element. This communicates our design intent and is remembered by the software. If the mainline geometry changes, the side road will automatically be shortened or extended to intersect the mainline geometry. Rules are what separate microstation and civil geometry. As we just discussed, many of the same tools such as snaps and manipulation tools are used for both microstation and civil geometry elements. You can even use AccuDraw or Civil AccuDraw with both microstation and civil geometry elements. But the big difference is once a microstation element is created, it doesn't remember how it got created. There's no design intent, there's no rules. The Create Civil Rule Feature tool adds rules to microstation graphics, turning them into civil geometry elements, where they have all the same capabilities as any other civil geometry element. The Create Civil Rule Feature tool is simple to use. Just select the microstation element and you're done. The Create Civil Rule feature works for both horizontal and vertical geometry. There are several microstation tools that can be useful with civil geometry. The Extend Line, Trim to Intersection, and Trim to Element modify tools each create rules that define the length of elements relative to other elements. The rules created by these modify tools are honored when updates are made. Insert Vertex tool allows you to place a point along a geometry line, but it does not add a curve. The curve is added in the second step using civil geometry curve tools. While this is a valid workflow, a better workflow is to use the Insert Curve, which is in Civil Geometry tools. The Delete Vertex tool removes only the curve if a curve exists. If a curve does not exist, it removes the vertex. Therefore, to completely remove a vertex that has a curve, the tool is run twice. First remove the curve, then remove the vertex. The Drop tool drops a complex status of civil geometry alignment back to its individual curves and lines. Centerline geometry will be required to satisfy design standards to ensure safe and effective roads are being built. The Open Roads technology includes tools to evaluate and report geometry that does not satisfy the requirements. Several imperial and metric-based design standards are delivered with the software. Additional standards can be added to meet your organization's specific requirements. This course teaches how to use the design standards. Modifying or setting up new design standards is outside the scope of this training. A design standard can be set active when creating geometry elements. When the active design standard toggle is enabled, minimum curve radii and other parameters will be automatically set in the Create Geometry tools. While this can be powerful for some design workflows, it can become cumbersome in much of your work because you probably do not want to evaluate every geometry element you create against the design standards. Only the final, complex geometry alignment typically needs to be evaluated. A good workflow is to assign a design standard only to the final, complex geometry alignment. When a design standard is violated, feedback is provided as an icon on the element where the problem is located and in the Civil Message Center. Design standards do not force you to use minimum or recommended values. They alert you when your values do not meet the recommended standards, but ultimately the engineering decision which values to use is up to you. A design standard is associated and stored as part of a geometry element. Verify that a design standard is associated with the geometry element in the Element Information window. The design standards appear immediately below the element in the top portion of the window.